Hello everyone, my name is Ahmed Al Jafari, and today I will be showing you the process of me analyzing um, this set of spectra to come up with a structure that fits all peaks in the different spectra. My group is group 1, and I will start by showing you the IR, which I have used to obviously decide whether or not I have functional group in the final structure. Starting from left, I have we have a peak at closer to 3000, and that indicates that we have an sp3 hybridized um, CH bond, which is proven by this table that I've provided here. You can see that the range is between 2900 to 2700, which is more accurate. It's not fully on 3000, sort of closer to it. And then moving down the middle, um, we have a peak right in between 1500 and 2000, around 1750, 1700. And that indicate, according to this table, C double bonded to an O. I have further tried to check what type of C double bonded to an O I have here, and for that exact reason, I used this other table, um, and it was closer to the ester range, which is 1735 to 1750. I estimated the bond to be at 1750. Um, and then finally, I have, let me go back to that table. We have a final peak around 1200, and that indicates a C single bonded to an O. That is further proved by this range of frequency right here, 1200 to 1180. We have 11 and then 1200. So this indicates that I have a C single bonded to an O. I then moved on to the CNMR to understand the nature of my carbons, and I have used this table to interpret the different peaks. We have a peak around 173, 174, I estimated it to be, and that indicated that I have a carbon double bonded to an oxygen. Sorry, not this one. Around this range right here. Again, it doesn't really show whether it's carboxylic acid, an ester, or carbonyl. Um, so I estimated it again to be um, it's just in right in between. It's not low like close to the 160, and it's not high enough to the 180. It's sort of the second half, closer to the 180, but just off 170. So it kind of shows that it's like right in this sweet area of an ester. Um, and then moving down, we have another peak right around 60, 61. That indicates, just move myself a little. That just indicates that this carbon, it's just right in between um, these two. Obviously, we don't have any of these molecules in our structure, or sorry, the molecular formula that was given. So I concluded that that bond is an sp3c single bonded to an O. Moving down, we have 4 more carbons left. Obviously, the closer the carbon is to the carbon that is connected to an electronegative atom in the structure, the down further the ppm of the peak is going to be. So I estimated these first two to be CH2 just because of how close they were, how close the peaks are on the spectra to the C double bond to an O. And these last 2 carbons, I estimated them to be the further away um, from the C single bonded to an O, just because of how it's in the range of between 20 and 0, not really in the range of like 25 to 40, which these ones are. So I estimated it to be a CH3. I then moved on to the HNMR, and I used this specific table um, to interpret my peaks. Starting, I had a peak, and I will show you the tables that I have came up with after I finish explaining them on the spectra itself. We have a peak around 4.1 to 4.2, and that really just a little bit off of 4.0, and that fell in with the CH3 single bonded 2-0. Then moving down, we have a 2.3, 2.2, and that fell with the a hydrogen that is bonded to a carbon that is bonded to another carbon, which is bonded to a double oxygen. I know I drew C double bonded to no, but I did not. I didn't mean for it to mean that specific carbon, because obviously in this situation that carbon wouldn't have a hydrogen, so um, that peak would not make sense for a carbon double bonded to an oxygen by itself. Rather, it's the hydrogen of the neighboring carbon of the carbon double bonded to an L. And then we have a sextet. I know I butchered that name. I'm sorry about that. Down around 1.7 to 1.8 down here. That indicated that fell right in between the CH and the CH2 ranges right here. It's a little bit closer to the 1.4, a little bit lower than the 1.5. So I estimated it to be a 1. But right in between the 1.2 to the 1.5 to be a CH2. And then finally, we have a really high peak around 1.2 to 1.3, and that also indicates that we have a CH3 according to the integration of the peak itself. And finally, we have I estimated that peak to be 0.9. I haven't really memorized the numbers, but I will further justify them in the table below. We have a peak shown around 0.9, so I estimated that to be a CH3 as well. Moving down, I started by calculating my degrees of unsaturation, just to know if my structure will have a double bond, whether it would be, a C double bonded to an O or an aromatic ring. My degrees of unsaturation came out to 1, meaning that I must at least have one double bond in the structure. I have written down the peaks of the data that I have, the data of the peaks that I've collected from the IR table, the IR spectra, and that gave me a C single bonded to an H, sp3, hybridized, and at 1750 I estimated that to be an ester. 1200 to 1000, right in between that range, was the last peak I estimated to be a C single bonded to an O. And then this is the interpretation that I have gathered from the CNMR. As I have mentioned previously, the 173, the very far peak on the spectra indicated that I have a C double bonded to an O. And then following, I had an sp3C single bonded to an O, followed by CH2, the very close double peak, not very close double peaks, but the one closer to the C single bonded to an O, and the very close last two peaks of CH3. Lastly, I wrote down the chemical shifts, which have further approved my conclusion from the previous two tables of having a C single bonded to an O. Sorry, and a hydrogen that is bonded to a C that is single bonded to an O. And then at 2.3, I had so that first bond is a quartet, which is this carbon right here. The neighboring environment has 3 hydrogens, and following the rule of n plus 1 of the integration, that would give us 3 plus 1, which would make the specific peak for this uh, hydrogen environment quartet. Coming down, we have a 2.3, which was a hydrogen that is bonded to a carbon which is bonded to double oxygen. I know it sounds confusing, but this would make it a better example right here. It's sort of in between the 2.0 to 2.6 range of chemical shift, ppm. And that was a triplet because the neighboring hydrogen, as I have mentioned before, has an n value of 2, which would result in a 2 plus 1 equaling 3, gives us a multiplicity of triplet or 3. And following, we have a 1.7 um, carbon with 6 hydrogens, or and a multiplicity of 6 in the surrounding hydrogen environments, and that would be this carbon right here, which would have 2 hydrogens on this side and 3 hydrogens on that side. An n value would be of 5, and 5 plus 1 is 6, obviously. And then the following 2 would be our 1.2, our last CH2 of sorry, 1.2 would be a triplet, which would be this carbon right here. That would be this carbon right here, just because it would be closer to the oxygen. Therefore, it would have a higher peak than that further away carbon, just because of the electronegativity pull from the oxygen. And that one is triplet because obviously the neighboring carbon has 2 hydrogens. And finally, we have a 0.9 indicating the final CH3 that we have here, which is also a triplet because of the neighboring carbon, which has 2 hydrogens as well. As we see, we do have an ester in the final structure, which further justifies and proves the information that I've gathered from the IR spectra and the chemical shift from this 13-CNMR and finally the HNMR. And I believe the name of it would be ethyl butyrate. Thank you very much for listening. That was my presentation for today.